So the main objective of this lab is to design an experiment to test a claim that answers this question. And this question basically, can we count matter at the molecular level and the atomic levels? So there are two things I gave you, and there are two things that I gave you in terms of getting you started with designing the experiment. First is the scale, that's the equipment, and then we have the substance that we are going to look at. In this case is chalk. And chalk is basically calcium carbonate. And part of the procedure is you are going to come up with a tweet message between 200 to 240 characters that you are going to write with this piece of chalk. And then you're going to determine, is it even possible to determine how many molecules of chalks that you use to write that tweet messages? Or how many atoms of each of the elements are used to write that tweet message? So, of course, if we look at this, we know that chalk will be used up in the process. By looking at this concept, we realize that you have a scale. What do we use a scale for? Well, we use a scale to get the mass of the chalk. So this equipment allows us to get the masses of the chalk. Now, if we look at this, when we have a piece of chalk right here, let's assume that's a piece of chalk. This piece of chalk, of course, would have an initial mass. And what happened to this piece of chalk when you use it to write your message? Of course, you're going to use the chalk to write it, and therefore, the mass is going to decrease. And notice it's going to decrease, right? So we can consider this as your final mass. There you go. And just to give an example, one of the students has 5.0 grams of chalk initially, and after he used to write his 240 character message, it turned out we have 4.9 grams. So what's happening there? How much chalk is being used? And all you do is take the initial minus final, give us 0.1 grams CaCO3 used to write your message. So the design of the experiment basically saying that along the line that you record down the mass of the chalk initially, and then you write your message, and then you get the final mass. The difference in the two mass will give you how much mass you use. And that is extremely simple, isn't it? But many students will struggle with this because they have never been exposed to the rigor of designing their experiment. So if you didn't get this far, don't worry, we will have different opportunities later on throughout the year that you will design an experiment. And let's go back and continue analyzing the data from the lab. Well, in this case, outline the step that you would need to convert from grams to molecules of calcium carbonate. And basically all it's saying that if you know how many grams of calcium carbonate that you use to write your message, can you find that, or can you convert to molecule? In this case, just a basic stoichiometry problem where you are given 0.1 grams of calcium carbonate, and we are looking for question mark molecules of calcium carbonate. And if we look back at the stoichiometry flowchart, where do we always start from? You're given. In this case, this is where you start. And where do you end? At the molecules of A. And where do you end? Of course, we are going to molecules of A. That's because the chemical hasn't changed. So this is where you end. To start from mass in terms of gram all the way to molecules, what do we need? We need to go down. That's one conversion factor. And we need to go across. That's the second conversion factor. And of course, we're going to write down what we are looking for. We're looking for molecules of calcium carbonate equal to, starting with our given as always, in this case, how much grams of calcium carbonate did we use? 0.1 grams of calcium carbonate. Time our very first conversion factor, which is this one right here, 1 mole of A equal to the number of grams of A. And times the next conversion factor, which is 1 moles of A equal to 6.02 times 10 to the third molecules of A. And we all know what is A. Your A is your chemical, which is calcium carbonate. So I'm going to substitute that in. All the letter A is calcium carbonate. Now, for this conversion factor, both of the measurements are complete, except for this one, the number gram. What does that number gram represent? Well, that is the molar mass of calcium carbonate. You can Google for the molar mass of calcium carbonate, or you can use the periodic table to calculate. So I'm going to write out. So CaCO3. In this case, Ca there's only 1, C there's 1, and O there are 3. And I remember the mass for calcium on the periodic table, 40.08, and carbon is 12.01, and oxygen is 16.00. And 40.01 for the total mass of calcium, carbon is 12.01, and then for oxygen, 3 times 16, that is what? That is 48.00. And we add them together, what do we get? We have 100.09. And that right there is 100.09. So we have our conversion factor. That's how you would outline it to solve for how many molecules of calcium carbonate. So let's just solve this, okay? So we have 0.01 grams of calcium carbonate times our very first conversion factor. Since this is grams of calcium carbonate, the bottom one must be grams of calcium carbonate. Exactly 1.09 grams of calcium carbonate. And on top must be the leftover on the other side, which is 1 moles of calcium carbonate. And then we are done with the conversion factor. Now we multiply to the next one, and notice how grams of calcium carbonate cancel out. Now if that's moles of calcium carbonate, down here must be mole calcium carbonate, which is exactly this one right here. And on top would be the leftover, which is 6.02 times 10 to the 23rd molecules of calcium carbonate. And look what happens to moles of calcium carbonate, it cancels out. All we have to do is now plug in the calculator. 0.1 divided by 100.09, that's because it's on the bottom, time 6.02 times 10 to the 23rd. 6.02 E23. That's because it's on top. And what we have here is our final answer turned out to be, let me write it down here, equal to 6.03 times 10 to the 24 molecules of CaCO3. And that's how you take your grams of calcium carbonate that you use and convert it to molecules. Now, for this part, it's going to ask us to count at the atomic level, basically count the atoms. So basically, if we look at this flow chart right here, right, we look at calcium carbonate, CaCO3, and can we count how many atoms of calcium being used? Which I described down here. So let's look at this. Of course, we are starting from what? Grams of, well, exactly number of grams of calcium carbonate. And we're going to go to molecules. Well, specifically, we're going to go to atoms of calcium. We're going to go to atom of carbon and atom of oxygen. We have to do them individually, okay? So if that's the case, we really have to go from grams of A, okay, all the way to atoms of B. So we go back to the flow chart. We pretty much start from right here, but we're not going to end on side A. But what we're going to do is we're going to go down, we're going to go across, and we're going to go across over here, and then we would have our atoms of B. So that would be how we convert from mass of A all the way to atoms of B. So if I were to write this in terms of describing how would I solve it, I would have Of course, I'm going to look for atoms of B. Okay, and that would equal to my starting values, number of gram used of calcium carbonate, times the very first conversion factor, which is right here. Okay, 1 moles of A equal to the number of grams of A. So we have 1 mole of A equal to the number of grams of A, which we know it is 100.09, because A is your given chemical, CaCO3, and here would be CaCO3 as well. Now we're going to continue and multiply the next conversion factor, which is this one right here. So this first, second, and third. So for that one, we have number of mole A equal to the number of mole B. Well, what is A and B? A is your calcium carbonate, and what's a B? B is whatever you're looking for, calcium, carbon, or oxygen. Okay, it doesn't matter. Now we're going to time the last conversion factor, which is 1 moles of B time, which is 1 moles of B equal to 6.02 times 10^23. In this case, atoms of B. So we have 1 mole of B equal to 6.02 times 10^23, which is represented by E, atom of B. And that would be the outline how you would solve for specific atom. Let's do one example for calcium, and then you can do the rest by itself. Well, of course, in this case, I'm going to look for atoms of calcium. And how many grams of calcium carbonate did I use to write out my tweet message? In this case, it is 0.1 grams of calcium carbonate. And time, our first conversion factor over there, 1 moles of A, we know exactly, is calcium carbonate, equal to the number of grams of calcium carbonate, which is 100.09 gram of calcium carbonate. Time, our next conversion factor, which in this case is the number of moles of calcium carbonate, and of course this is always 1. 1 mole of calcium carbonate equal to what? How many moles of B? B in this case is going to be your calcium. So in CaCO3, how many calcium do you see? Just 1. So it's 1 mole of calcium. And that's pretty much it. Time our next conversion factor, which is 1 mole of B, that's calcium, equal to 6.02 times 10^23 atoms of B. What is B again? Calcium. Now we just rewrite this as a fraction so that we can simplify our conversion factor. So in this case, 0.1 grams of calcium carbonate time, if this is grams of calcium carbonate, down here must be grams of calcium carbonate as well, which is 100.09 grams of calcium carbonate. On top will be the leftover, which is the other side, the other measurement, 1 mole of calcium carbonate. And this cancel out. So now we move on to the next conversion factor. Time, again, this one is done. Now we move into this one. Now we have moles of calcium carbonate. So moles of calcium carbonate must be on the bottom. And how many? 1. And on top is the leftover, which is 1 mole of calcium. And it makes sense. Moles of calcium carbonate cancel out. And then we multiply the next conversion factor. This one's done. Now we multiply the next conversion factor. If this is moles of calcium carbonate, down here must be moles of calcium. And if we look at the next conversion factor, if this is moles of calcium, down here must be moles of calcium as well. That way they cancel each other out. And on top is a leftover, 6.02 E23 atoms of calcium. And then all you have to do is plug into the calculator. And what do we have? 0.1 divided by the number on the bottom, which is 100.09. Do we have any number on the bottom next? Nope, because it's all 1. And time, 6.02 E to the 23rd. And what do we have? We have 6.02 times 10 to the 24th. And that's pretty much it. In this case, atoms of calcium. So you would do the same thing for carbon and oxygen, okay? And the last thing is you are going to write your CER, where this one you're going to make your claim. And this one is your evidence which you collected from the lab, or evidence from the flowchart, and reasoning. Basically, how does your evidence support your claim? So this, how does it support that? So can I give you an example of a claim? Well, an easy one would be like this. Starting with using the one of the starter sentence I gave to you on the paper. Well, one of the starter sentences starts something like this. According to the evidence from my lab, I conclude that it is possible to count atoms at the molecular level and the atomic level. Boom. That's one claim. Or how about I'll give you another one. Well, according to my observation from the lab, I conclude, or I can determine that it is possible to count matter at the molecular level and the atomic level. How about another one? Based on the lab that I designed to determine how many molecules of calcium carbonate is used to write my tweet message, I can conclude that it is possible to calculate for how many atoms or how many molecules of the compound. And of course, for the evidence, it doesn't have to be paragraph. It could be problem that I just did for you up here. And that would be evidence in terms of supporting your claim. All you need to add a little bit of annotation to it, and then you are done.